just under 2 weeks apart in 1977 from Cape Canaveral and together cost around $900 million to develop and deploy. Voyager 1, humanity's most distant emissary, is a spacecraft that has defied time, expectation, and imagination for nearly half a century, continuing to transmit whispers from the edge of the cosmos that challenge our understanding of where we come from and where we are going. Launched in 1977 during the height of the space race, and originally designed for a 5-year mission to explore the giant planets of our solar system, Voyager 1 quickly surpassed its original mandate. It performed breathtaking flybys of Jupiter and Saturn, delivering images and data that transformed planetary science forever. Its close encounters revealed the tumultuous atmosphere of Jupiter, the volcanic activity of its moon Io, the swirling rings of Saturn, and the complexity of Titan's thick haze. These achievements alone would have secured Voyager 1's place in history. But the spacecraft's journey did not end with the gas giants. Instead, it pressed on, climbing out of the gravitational well of our solar system and embarking on a mission no one had ever attempted: to plunge into the unknown domain of interstellar space. Decades later, in 2012, Voyager 1 officially crossed the heliopause, the invisible frontier where the influence of the Sun ends and the interstellar medium begins, becoming the first human-made object to leave the solar bubble behind. This crossing marked not just a technical milestone, but a philosophical one, symbolizing humanity's first step into the vast sea of the galaxy. Yet, even more remarkable is that more than 10 years after that historic moment, and almost 50 years after its launch, Voyager 1 is still speaking to us. And what it is saying has left scientists, philosophers, and visionaries stunned. The latest transmissions from Voyager 1 are unlike anything we expected. Its instruments, though built in the 1970s and far less powerful than even a modern smartphone, have been detecting strange persistent fluctuations in the magnetic field at the edge of interstellar space. These variations, while faint, are not random. They are rhythmic, patterned, and consistent, almost as though the spacecraft were tuned into some larger system of pulses that ripple through the galaxy itself. According to long-standing theoretical models, interstellar space was supposed to be relatively calm once the Sun's influence gave way to the broader magnetic field of the Milky Way. Scientists imagined Voyager 1 would encounter a uniform environment, steady and unchanging, as it drifted through the interstellar medium. But instead of tranquility, Voyager is hearing a kind of cosmic music, waves, fluctuations, and disturbances that defy our simple models of what should exist beyond the Sun's reach. These patterns have led researchers to reconsider the very nature of the heliopause. Instead of a static wall marking the boundary between solar and galactic space, the heliobubble may be more like a dynamic membrane, a breathing interface that flexes, ripples, and responds to forces far beyond our solar system. If this is true, then the picture of our solar system as an isolated island in a placid galactic sea must be abandoned. Instead, we may live inside a cosmic harbor whose shores are ceaselessly battered by the tides of the Milky Way. One emerging hypothesis is that the magnetic disturbances Voyager 1 is detecting are driven by energy streams or charged particle flows that originate far outside our local galactic neighborhood. These currents could be the fingerprints of supernova explosions, gamma-ray bursts, or even the vast and mysterious galactic magnetic field threading across thousands of light years. If so, then Voyager is detecting not just local noise, but the echoes of distant cosmic events, waves traveling through the galaxy that eventually reach the fragile membrane of the heliopause. This interpretation suggests that the solar system is not a sealed bubble, but a participant in a larger interconnected galactic system where energies and forces flow back and forth. Such an idea aligns with cosmological models of the cosmic web, the vast scaffolding of gas, dark matter, and energy that stretches across the universe like an immense three-dimensional spiderweb. Until now, this structure has largely been observed indirectly through the clustering of galaxies and the gravitational lensing of distant light. But Voyager 1's findings may represent the first direct local evidence that this cosmic lattice is not merely an abstraction, but a tangible system we are embedded within. The implications of such a possibility are staggering. Our solar system, and therefore, humanity itself, is not floating alone in silence, but but is tethered to and shaped by invisible galactic structures that bind the stars together. For some scientists, these magnetic patterns are not merely interesting. They are paradigm-shifting. They hint at a universe far more dynamic and interconnected than we once believed. But beyond the scientific interpretations, a more speculative and daring idea has emerged. If magnetic fluctuations can persist across light years, carrying coherent patterns of energy and rhythm, then might they serve as a medium for communication? Could Voyager 1, in its fragile endurance, have stumbled upon the faint heartbeat of a universal signaling system? Some researchers have dared to ask whether the patterns Voyager is hearing might be artificial echoes of an advanced intelligence using the galaxy's own magnetic framework as a communication channel. Traditional radio transmissions fade quickly across astronomical distances, but embedding information in naturally occurring galactic fields could in theory serve as a longer-lasting and more efficient method. While most of the scientific community remains cautious, preferring to focus on physical and natural explanations, the mere fact that such questions are now seriously considered reflects the profound impact of Voyager's discoveries. What once sounded like the realm of science fiction, messages hidden in the cosmos, sent through currents that bind the galaxy together, now hovers at the edge of scientific plausibility. Even if the signals are natural, their implications remain extraordinary. A helipause that flexes and shifts in response to distant galactic pressures means our solar system is connected to the galaxy in ways we had never imagined. Cosmic weather may not be limited to solar storms and solar winds, but could include influences from events occurring thousands of light years away. A supernova shock wave, a fluctuation in the galactic magnetic field, or a surge of cosmic rays could ripple outward, subtly shaping the heliosphere and altering the conditions of space near Earth itself. This realization has sparked conversations about the helipause not as a protective shield, but as a sensitive cosmic interface, one that records and responds to the wider galactic environment. In this sense, Voyager 1 is not merely a probe of interstellar space, but also an early warning system, a far-flung antenna picking up whispers of the universe's heartbeat long before those influences reach the inner solar system. The scientific community has responded to these revelations with both excitement and urgency. Researchers are poring over Voyager's faint data streams, comparing them to models of interstellar turbulence and galactic magnetism, searching for clues that can explain the anomalies. Voyager 2, which crossed the helipause in 2018 along a different trajectory, provides a crucial second data point. Its measurements, while not identical, confirm that the helipause is not uniform, but asymmetric, shaped by pressures that vary depending on direction and galactic conditions. This reinforces the idea that the heliosphere may resemble not a bubble, but a comet-like structure with a distorted tail trailing behind it. As the solar system moves through the galaxy, Voyager may first have crossed into a particularly active or sensitive region, allowing it to detect disturbances that Voyager 2 has not yet encountered. Together, the two spacecraft paint a picture of a boundary that is alive, shifting, and shaped by forces far beyond our Sun. The broader implications of these discoveries extend far beyond astrophysics. Elon Musk, among other visionaries, has publicly expressed fascination with Voyager's data, interpreting it as a signal that humanity must accelerate its efforts toward interstellar travel. To Musk and others who dream of humanity among the stars, Voyager 1 is not just a relic of the past, but a beacon of the future. Its faint, decades-old instruments have hinted at currents of energy and structure that may one day be harnessed for travel or communication. Just as ancient sailors once learned to navigate by winds and currents, future explorers might learn to ride galactic tides propelled by forces we are only beginning to detect. Today, this sounds fantastical, but so too did the idea of flight before the Wright brothers, or space travel before Sputnik. Voyager's discoveries could serve as the seed of technologies we cannot yet imagine, inspiring the next generation of spacecraft designed not merely to observe, but to navigate and perhaps even exploit the hidden highways of the cosmos. Meanwhile, the practical work of science continues. NASA, ESA, and other institutions are considering follow-up missions to build on Voyager's legacy. One of the most promising concepts is the Interstellar Probe, a next-generation spacecraft envisioned to launch in the 2030s. Unlike Voyager, which was repurposed for interstellar exploration after its planetary mission, this probe would be designed from the outset to study the heliosphere, the interstellar medium, and the galactic environment beyond. Equipped with advanced instruments far more sensitive than Voyager's, it could map the outer heliosphere in 3 dimensions, measure interstellar dust and plasma with unprecedented precision, and probe the magnetic field in detail to test whether the anomalies Voyager detected are signatures of turbulence, cosmic filaments, or something stranger still. Such a mission would not only extend humanity's reach into interstellar space, but also help answer some of the deepest questions raised by Voyager 1. Is the helipause a wall or a membrane? Are the fluctuations natural or artificial? Are we adrift in a calm void? Or are we participants in a living galactic network? What makes Voyager's journey so profound is not just the data it collects, but the symbolism it carries. Here is a machine built in the 1970s with less computing power than a modern calculator. Still operating more than 23 billion kilometers from Earth, powered by radioisotope generators that continue to hum decades past their expected lifetime. Its transmissions, faint whispers crossing the abyss, remind us of the resilience of human curiosity. Each bit of data is a triumph of engineering and imagination, a testament to what humanity can achieve when driven by the urge to explore. Voyager 1 is more than a spacecraft. It is a time capsule of human ambition, carrying with it the golden record, a message from Earth to the stars, encoded with music, greetings, and images meant to represent the diversity of life on our planet. It is both a scientific instrument and a cultural artifact embodying our species' desire not only to understand but also to be understood. Eventually, of course, Voyager 1 will fall silent. Its power supply will dwindle, its instruments will cease, and it will drift endlessly through interstellar space, a cold relic of a civilization on a small blue planet orbiting an ordinary star. But its legacy will not end with its silence. The questions it has raised about the structure of the heliosphere, the dynamics of galactic forces, and the possibility of interstellar communication will reverberate for generations. Even in its fading signal, Voyager continues to remind us that exploration is not about destinations, but about perspectives. It teaches us that the boundaries we imagine between solar system and galaxy, between science and philosophy, between the known and the unknown are porous and shifting. In the faint magnetic fluctuations it detects, we hear not just physics but poetry, not just data, but an invitation to dream bigger. Voyager 1 tells us that we are not alone. Not in the sense of aliens necessarily, but in the sense that we are woven into a cosmic fabric larger than we can yet comprehend. As long as Voyager drifts among the stars, humanity drifts with it, reaching out with trembling hands toward the infinite. Its mission, born in the age of analog computers and rotary phones, has evolved into a quest that touches the very limits of reality itself. What lies beyond the helipause may reshape our maps, our science, and our sense of belonging in the cosmos. The fluctuations it records may turn out to be turbulence in the galactic medium, or they may reveal the first fingerprints of the cosmic web's influence at a local scale, or they may even, in the most speculative dreams, be the faint echo of intelligence. Whatever the answer, the fact that a small spacecraft built decades ago can still challenge our deepest assumptions is proof of the enduring power of exploration. Voyager 1's journey is humanity's journey. Its discoveries are our discoveries. And in its fading signal, we hear not just the cosmos, but ourselves.